So today I'm going to talk about a new language feature that we are adding to OCaml in order to simplify concurrent programming. Right? And the context for this talk is Multicore OCaml. As was mentioned in the introduction, so Multicore OCaml aims to add native support for concurrency and parallelism to OCaml. And the thing that we do in Multicore OCaml is to clearly separate out concurrency from parallelism. So we define concurrency as overlapped execution of tasks, where one task may switch control to another task by yielding, and then maybe the other task yields control back. And this happens over and over until all of the tasks are completed. We define parallelism as simultaneous execution of tasks in time. Right? And in keeping with this separation, we have two distinct mechanisms for expressing concurrency and parallelism in OCaml. For concurrency, we have what are known as effect handlers. And for parallelism, we have a separate mechanism called domains. And the focus of this talk is going to be on effect handlers. Right? So at the beginning, it might be useful to actually set this out straight, right? So concurrency is not parallelism. Whereas parallelism is a performance hack, concurrency is a program structuring mechanism. Right? So what's an example? A good example is operating system threads. Right? Operating system threads give you both concurrency and parallelism, but they are typically too heavyweight for concurrent programming. What do I mean by this? Imagine writing a web server where you sort of want to organize it in a nice way, and you think, okay, I'm going to spawn a operating system thread for every incoming request. Right? This is a terrible idea. This web server will not scale, even though it's a nice program structuring mechanism. This is because operating system threads also bring in parallelism, right? And you pay the cost for parallelism where you typically need concurrency. And I mean, this is not a new fact. A lot of programming languages provide specialized mechanisms for concurrent programming. These come in variety of different forms: async await, generators, coroutines, etc., etc. And many languages often include lots of different primitives in the same language, right? For example, JavaScript has async await, generators, promises, and there is also callback-oriented programming. And all of this might appear in the same JavaScript application. Right? And let's focus on OCaml for the moment. So what is the state of concurrent programming in OCaml? OCaml does not provide a primitive support for concurrent programming. That does not mean that you cannot write concurrent programs in OCaml. We do have battle-tested libraries such as LWT and async for concurrent programming in OCaml. If you don't know anything about async and LWT, they essentially let you do callback-oriented programming, right? But they sort of hide it under nice monadic syntax. Even though they use monadic syntax, they are not true monads because they do not satisfy monad laws, but that's a different story. But really what the issue is that because at the end of the day, you are doing callback-oriented programming, you suffer many of the pitfalls of callback-oriented programming. In particular, because you are threading together callbacks, you do not have backtraces anymore. You cannot get backtraces. You cannot use inbuilt exceptions in OCaml. Exceptions go to the wrong place. You have to use monadic syntax, right? And in a language like OCaml, which has ambient effects, using monadic syntax seems a bit clunky, right? And OCaml does not have higher kinder types. So if you have two different monads, you cannot sort of easily combine them together. And also operationally, right? So if you're using callbacks for programming everywhere, you tend to allocate too many closures. And this puts an impact on the garbage collector. So other languages do have better abstractions for programming concurrent programs. In particular, if you take Go, it has nice Go routines, and GHC Haskell has threads, both of which are a form of lightweight threading, right? And lightweight threads are distinguished from heavyweight threads in the fact that these threads are managed by the language runtime. So they are the cost of typically creating them and destroying them is really cheap. And you can map these lightweight threads onto operating system threads as per need, right? So they do have other nicer mechanisms in other languages. So when we were designing Multicore OCaml initially, we thought, okay, should we add lightweight threads to OCaml so that we can write expressive concurrent programs? So it turned out that this was at a time when this new mechanism came on our radar called effect handlers, which turns out to be this secret sauce, right? So which helps us write concurrent programs, but also much more. What effect handlers are, in fact, is a mechanism for programming with user-defined effects, right? And they serve as a modular basis for non-local control flow mechanisms, like all of it, right? So you can implement exceptions, generators, lightweight threads, promises, asynchronous IO, coroutines, and anything else just by having effect handlers in the language. So you can encode, once you have effect handlers in the language, you can encode all of these as just libraries. And to give you a one-line summary of what effect handlers are, what they provide you is a first-class mechanism of restartable exceptions, right? We understand exceptions. Exceptions sort of indicate an exceptional condition, and it is handled by the handler. So if you had the ability to go back to where the exception was raised, but also not having to do it immediately, you can choose to sort of squirrel away this context for later and come back and resume it later. That is what effect handlers provide you. And similar to exceptions, the act of performing an effect is separate from handling it. So for a given effect, you might interpret that particular effect in a variety of different ways. Right. In order to make the ideas more concrete, let's look at an example here. So in this example, in the first line, what I've done is declaring an effect E, right? And the string after the colon says that when you perform this effect E, you're going to get a string value back. So effect handlers allow you to run computations in the context of a handler. And this handler is similar to a exception handler, except that it has this other argument K, which we'll come back to. Right? And just like exception handlers, you pattern match on the effect here. So the thing that effect handlers bring you is this ability to perform an effect. And what happens when you perform an effect is that you sort of suspend the current computation, right? And the control switches to the matching handler. And in the matching handler, in addition to the effect that you actually pattern match with, you get the delimited continuation, the context that is between the point of perform delimited by this handler as a delimited continuation, which you can use to continue this computation again, right? So really the real power of effect handlers comes from this delimited continuation. And once you have this delimited continuation, you can use the continue primitive to resume the suspended computation. And this delimited continuation is a first class value. You can store it in a data structure so that you can resume this later as well. So that's something about the syntax. Let's actually look at how this example works, right? By stepping through the example. And what I have on the left is the same example as earlier, but I show where the program counter is. And on the right, I'm going to show how the stack evolves as the program executes. And this evolution closely mirrors how we implement effect handlers in Multicore OCaml. So the program counter is just before the entry to the computation, right? And the stack is now in the main function. And once you enter the computation, the first thing that we do is to allocate a new piece of stack for executing the computation. And we also associate the effect handler along with this piece of stack, right? And we call this combination a fiber, right? And this piece of stack is really small. In our implementation, it's just 32 words in length initially, and it dynamically grows on demand. And the other thing that we do is we also establish a parent pointer from this new fiber to the previous fiber, so that we sort of have this stack discipline between all of the fibers that are currently under execution. Point, the first thing that we do is to allocate a small continuation object. So this is one word in length. And what this continuation object points to is the current fiber, right? And we destroy the parent pointer that pointed from the comp to main fiber. And after this, what we do is we dynamically search for the matching handler for this effect E. And once we find the match, we switch to the matching fiber and continue executing the body of the handler. So the body of the handler is here. So our program counter switches there. And we have also obtained a reference to the continuation. which is essentially a pointer to the fiber, right? And you print 1. And now we are at a stage where we are going to resume the continuation, right? The first thing that we do here is we sort of say erase the pointer from the continuation to the fiber. So what this means operationally is that our continuations are one shot. And the reason that they are one shot is that it is well known that one shot continuations are really efficient to implement because we do not have to copy the frames around. So we choose one shot continuation for our implementation. So, and then what happens is that you want to go back to where you left off. So essentially stack pointer goes to the point of the top of the fiber, and then we re-establish the parent pointer, and our program counter goes back to where it left off. And because we continued with the value 2, that is the value that is returned from here, and we print 2, right? And then now we are at a stage where we are going to print the last string, and we are going to finish the computation. So what happens now? So when you finish the computation, you return to the parent essentially. And the parent here is the parent where the point where you continue the continuation. So we return to the continuation of this continue primitive. So there was something left to do in the handler. So we return at that point. And the other thing that we do is we also free the stack that we've allocated at this point, right? Because the continuation is, the computation is done. So now you print 4 and the whole main function is done. So that gives you the sense of what we do operationally. And this closely mirrors how they are implemented as well. And of course, the handlers can be nested. So here is an example where we have two effects A and B, and we have a function foo, which runs the computation bar in handling the effect A, and bar in turn runs the computation baz handling effect B, and baz is going to perform A, right? And the stack at the point of perform is going to be baz, bar, and foo, right? And when you perform the effect, the matching handler is not the innermost one, right? It's the outermost one here in this example. So the program counter switches all the way to the matching handler. The stack pointer also switches to foo, foo's fiber. And what you get as a continuation is a continuation that points to the top fiber baz, which also holds the parent pointer, because that is also part of the computation the context that we need to have in order to resume the computation, right? So what this means in practice is that you have to linearly search through the handlers when effect is performed. And our handler stacks are shallow in practice. So in real examples that we've seen, this does not cause a particular performance degradation. Okay, so that's a bit about how they work. So what can we use them for, right? As we mentioned before, lightweight threading is the main example, right? So we are going to implement a very simple lightweight threaded scheduler with just two primitives. So you can fork a computation, right, which takes a unit arrow unit thunk and then spawns it off as a separate thread, or you can yield your current thread, right? And when you yield, you just get a unit value in return. Observe that yield or fork does not actually say how you are going to fork or yield, right? So this is left up to the handler to decide, and you can implement different scheduling policies for the same program, right? That is the benefit of separating out the effects from their implementation. So okay, so we've declared effects fork and yield, and fork takes an argument which is unit array unit, the thunk that you want to actually fork. And when you perform fork, you get a unit value as a result. When you perform yield, you just get a unit value as a result. We can run this in this main function. So this is the run function that implements the actual scheduler, right? We assume that there is a queue of continuations, right? And we want to run the main computation. So if you want to run the main computation, what we do is we first call spawn on this main computation. And what spawn does is it takes the computation and then runs it within the context of this handler, right? It is perhaps instructive to take a step-by-step look at what this does. So when you run the computation, if the computation runs to completion, so that particular thread is done, what you have to do, you have to look for other threads that might be available on the scheduler. So you call run next, right? And run next goes and dequeues any threads that might be available on the scheduler. If they are available, our threads here are essentially continuations, right? if there are continuations that are available on the scheduler, you simply continue the continuation with the unit value, right? And if there are no other threads available to run, then you're essentially done, right? So you return a unit value which returns which finishes this run function. If instead the computation here performs an effect yield, the continuation here represents the current thread, right? And you enqueue the current thread into the scheduler, and then you run the next thread from the scheduler. If the computation wants to fork, right, you get the F, which is the thunk that you want to run as a separate thread. You get K, which is the current thread. You enqueue K and then call spawn on F in order to recursively go and spawn that as a particular computation that you can run. Right? That's the entire implementation of a simple round robin scheduler. And you can wrap this effect in nice looking functions called fork and yield. And all they do is that they are a proxy for performing the effect. And they have nice types, right? So the fork will be unit array unit to unit, and yield will be unit to unit. And how can you use this? So here is a simple example which forks of two threads that print a message, yield, and print another message, right? And we have two such threads. And when you run this program using the run function that we just defined in the previous slide, what you get back is 1A, 2A, 1B, 2B. And the reason is that you first run the first thread, which prints end line, right, 1A, yields to the second thread, which prints 2A, which yields back to the first thread, which prints 1B, which runs to completion. And we pick the only other thread to run, which is the second thread, which prints 2B, and we are done. So the scheduler is very simple, but the important takeaway from the user point of view is that the code is in direct style, right? We do not have monads, but we have concurrency, right? That's a win for OCaml. The current state of OCaml is that if you want concurrency, you have to use a monad. And the second advantage is that the user code need not be aware of the fact that you are using FX underneath. So, so there is no mention of FX anywhere here. We just have plain old looking functions. And that is what effect handlers bring you. So next, let's move on to a more complicated example. So we are going to look at generators. And what are generators? Generators are this function to do non-continuous traversal of a data structure by yielding values, right? And generators are primitives in languages like JavaScript and Python. So just to give you an example, so here is a generator example in JavaScript. So if you want to say implement a function that might yield values, you have to explicitly use function star, right? And you declare a generator, and you can use the yield function, yield primitive, in order to yield values. And what this generator does is it first yields the argument value as it was passed, and then yields 10 plus the argument, right? And the way you use this generator is that when you call this function, you get a generator, and you can call next function on this generator to get the value. So when you call next first, you get 10 from here, which is the argument that was passed in. And when you call it again, you get the second value out, which is 10 plus 10, 20, right? So the point here is that the observation here is that function star is like a special syntax that is baked into JavaScript, right? And if you want to yield, you have to use function star. Right? And what we want to do is to automatically derive a generator from any iterator using effect handlers. So we are going to implement a generic procedure that sort of gives you a generator from an iterator, right? What do I mean by this? So here is the module that we are going to implement, right? And the way to read this is that give me any data structure, right? Any container that has some quotes, alpha values in them. Give me also this iterator on this data structure, right? That applies this higher order function on every value in this container, right? On this container, and then just returns a unit because iteration just has side effects. And what this module promises to give you back is a generator which says, given a data structure of the same type, I am going to give you the next function, right? And this next function has a unit arrow quote option. And the way to read this is you can keep calling this function over and over again to get values on demand, right? And when the iteration is complete, you just get none as a result. Okay. So that's the contract, right? and the entire implementation of this function is here. This implementation is a bit involved, but the important takeaway from this is that we have declared an effect yield in order to yield values from the iterator. And what we do in the body of the iterator is that for every value, we simply perform the yield effect to yield the value, right? And if the iterator is done, we simply return none. If the iterator some way. Of course, there are other things going on, but that's part of the implementation, right? This is not the code that the user is going to see. What the user of the generator is going to see is this, right? So suppose I want to implement a generator on a list. All I say is that the type is going to be alpha list and the iterator is going to be list iterator. I get an L module which gives you this generator. And what you can do with this L module is that you can call L.gen on a list 1, 2, 3. You get a next function out. When you call this next function repeatedly, you get one of the values on demand, right? As you would in the same order in which the iterator is written. So you get 1, 2, 3, and then finally none. And this is generic, right? So you can, given an iterator on any data structure, you get a generator out. So here is a binary tree, and here is an iterator that does in-order traversal on the binary tree, right? And applies this function f on the values in the tree. And you can make a generator out of this iterator by using the makegen module that we just defined earlier. And I have this helper function make, and all this function does is it returns a complete binary tree of depth n. So if you do make2, you get back this tree which has a depth 2 and values are 1, 1 at the lowest level and 2 at the higher level and so on. And of course, you can simply call generator on this tree. You get this next function, and when you call next, you get the values in order, right? In the order in which the iterator is defined. Since it is in order traversal, you get this value, right? And the key takeaway here is that this generator again, right, makes no reference to any effects and is generic, right? So you can sort of, if you can implement an iterator, you get a generator for free, essentially. So that was all about the dynamic semantics. What is the static semantics of effect handlers? Currently, the static semantics is very simple. We do not have effect safety, which means that there is no static guarantee that all of the effects that are performed in the program are always handled, right? So this is no worse than exceptions today in OCaml. So if you raise an exception, you do not have the guarantee that the exception will be handled. So you might have unhandled exception at the top level. So similar to that, if you perform an effect E at the top level without an enclosing handler, you just get an unhandled exception, right? So this is the state of the art in OCaml, Multicore OCaml implementation today. But FX systems are like open research problem, right? There are lots and lots of works that have languages that have done incredible amount of work in defining FX systems that are expressible, right? If you're interested in this topic, you should take a look at languages like F, Coca, Lynx, and Helium. Right? We are in fact working on an extension of OCaml that is equipped with an FX system. And the aim is that we will track both user-defined effects as we express using effect handlers, as well as built-in effects such as references, IO, exceptions, and so on. Right? Once we track built-in effects and user-defined effects, OCaml becomes a pure language in the sense of Haskell. Right? Divergence is still allowed, but you get an annotation on the function, right, which says whether it's an effectful function or not. So just to give you a sneak preview, this is how it is going to look, right? So today, if you implement this foo function, which just prints a string hello, all you get as a type for this inferred type for this function is unit or a unit. So in this new OCaml with an FX system, the type says that the input type is unit, the output is unit, but this function also performs this IO effect, right? that's on top of the arrow. And the syntax is still in the works, but there is some exciting new stuff that will appear as a result of effect handlers. Okay, so we've sort of covered all of the nice parts, right? So we've sort of said, okay, this is so great. Operationally, it's great. We're also going to get an effect system. But there is a big challenge which I haven't talked about, right? Which is retrofitting. So if you think about OCaml today, there are a number of serious OCaml users, right, who have millions of lines of legacy OCaml code. And all of this code is written without non-local control flow in mind, right? And if I tell any of those serious developers that, oh, you can have this fancy new feature, but you have to refactor all of your sequential code, right? This cost is going to be prohibitive for them. And they would rather say, okay, I'm happy with the state I am in. I don't want this new feature, right? So a guiding principle behind all of our development efforts is that we prioritize backwards compatibility before fancy new features, right? OCaml is always on the conservative side, and we sort of stick to this because it's worked out well for the language so far. What does that mean, right? So a good example is systems programming. So OCaml is a systems programming language, right? You can see a lot of serious OCaml programs that manipulate files, sockets, buffers, etc. And OCaml code happens to be written in this defensive style, right? To guard against the exceptional behavior in order to clear up resources. So what do I mean by this? Let's take a look at this very simple function that copies inputs from an input channel to an output channel, right? And the way it does it is very simple. So it has a loop. At each step of the loop, it reads in a line from the input channel and then outputs a string to the output channel. I mean, this is not the most efficient way to write this, but this is certainly how many of the programs are built, right? And this keeps going on until the input line raises end of file exception. And what this signifies is that there are no more inputs, right? And what we do is that we have an exception handler, right, which catches end of file and closes the input and input channel and the output channel, right, so that all of the resources are cleared. It is also the case that this input line and output string can raise sys error if the channel happens to be closed while this loop is in execution. So in which case, the code also has to handle arbitrary other exceptions, right? And make sure that the channels are closed, right? And re-raise the exception so that the caller of this function knows that something exceptional has happened, right? So this is typically how nice OCaml code that is defensive against exceptional behavior using resources is written. So the challenge for us is to sort of make this code transparently asynchronous, right? So input line and output string are synchronous functions. They are blocking. I want to transparently make this asynchronous, right? Without changing a line of code here. How can we do this, right? This would be like a really good test of saying, okay, you have all of this synchronous code. You can just magically get asynchronous IO from this. So here is how you do it, right? So you start defining effects for the input line and output string with the same signatures as the functions. So inline takes an input channel and returns you a string. Out string takes a pair of output channel and a string and returns a unit. You then wrap it with functions that have the same name and signature, right? Input line and output string, where all you do is just perform the corresponding effects, right? And you need to have a top level handler, right? Which we call run asynchronous IO, AIO here, which takes a computation F and then runs the computation in the context of this handler. What does this handler do? If the computation just returns with the value, you return the value. If the computation performs the effect inline, right? In an asynchronous IO world, you sort of have this event loop that is sitting underneath, right? So which is sort of saying, okay, what are all the IO actions that I need to do, right? And what are all the callbacks that need to be invoked when this particular IO action is complete. So that is what we have here. This function is like a proxy for saying that. So we register this channel for asynchronous input, and we say that K, the continuation that we captured here, is the callback that you need to call in order to resume this particular computation. And similarly for output string, right? We register this channel and the string for output, and we say that the callback associated with that is just the continuation here, right? And once you do that, all you do is call the run next function from the scheduler to execute other IO operations, sorry, other threads that might be that might need execution. So when the IO operation completes, all we do is we continue the continuation with the see the end of input was signified by this end of file exception, right? And we also had some logic for handling syserror exceptional cases, right? But if you sort of go back to all the things that we've seen, we've only the only mechanism that we have so far is to be able to continue a continuation with the value. Really, what we want to do is to continue a continuation by raising an exception so that the code that we saw in the previous slide continues to work. In order to do this, we introduce a discontinue primitive. And this works very similar to continue, except that what it says is when you call discontinue on K with end of file, it says, okay, I'm going to resume this continuation, but by resuming, I'm going to raise end of file exception at the point of perform, right? It appears as if the function that you call just raise an exception, which is precisely what we want for preserving backwards compatibility in that code, right? And the asynchronous IO scheduler uses discontinue to communicate exceptional cases, such as end of file and syserror, back to the computation. Okay, so that's discontinue. The other issue that we have to deal with is linearity of resources, right? Resources such as file descriptors, sockets, channels, buffers are all linear. So they are created exactly once and are destroyed exactly once. In OCaml today, right, if you call a function, it returns exactly once. It can return with a value or raise an exception. And defensive programming already guards against exceptional return cases, just as we saw earlier. But the funny thing that happens with effect handlers is that the only guarantee that you have is that the functions will return at most once. This is because it might be possible that you capture a continuation but never resume it, in which case this breaks resource safe legacy code, right? So in order to make this more concrete, let's look at an example again. So we declare an effect E, which when performed returns a unit. We have this function foo, which just performs E. And we have this computation bar, this function bar. For no reason, it opens this file, input.txt, it gets an input channel, and it then calls foo, right? And it says, okay, if foo returns with a value, I'm just going to close this input channel. If it raises any exception at all, I'm still going to close this input channel and then re-raise that exception so that my caller knows that something bad has happened, right? As far as today's OCaml is concerned, this bar function is doing everything right? So in order to clean up resources. Suppose I have this baz function, which calls the bar computation in this handler, right, effect E. But what it does is that it does not bind K. It does not even bind K. It does not resume it. So what happens here is that when this program is run, you open the input channel, right? You sort of open this file to get the input channel, and then you perform E. So the control goes all the way to this handler, which simply returns from baz, right? You are leaking the input channel now. This is bad, right? And this is bad because we are leaking resources for no fault of this bar, right? Which is like well-formed code today in current OCaml. So fixing linearity is tricky. Of course, you can use the garbage collector to install a finalizer on every capture continuation, but that's going to be expensive. So as a pragmatic trade-off, what we say is that we assume that every capture continuation is resumed exactly once, either using continue or discontinue, right? So this is sort of trade-off between performance and usability. We sort of lean towards performance here. And the reason why we make this assumption choice is that in many of the examples that we've seen before, and in fact in a lot of the real examples, the use of the effect handlers and handlers are sort of enclosed within the library, right? The user of the library does not need to deal with any of this. So that's why we make this choice. Okay, so that was linearity. And one more thing that we have to consider for backwards compatibility is OCaml's excellent compatibility with the debugging and profiling tools. So today, you can debug OCaml to some extent, to a certain extent, using GDB and LLDB, but you can also use perf to profile OCaml programs, right? And all of this is thanks to OCaml compiler emitting correct dwarf bytecode for stack unwinding, right? So dwarf is this debug format for expressing how to unwind your stack, but also find variables and so on. But OCaml does not do that. OCaml currently tells using dwarf bytecode how to unwind the stack, right? This is a useful feature because it allows debugging with GDB and perf. But observe that with effect handlers, we've sort of changed the stack layout. We have this fibers now, and our stack discipline is sort of interesting, right? Let me put it that way. So, so one thing that Multicore OCaml does is that it preserves stack unwinding even across fibers. Right? So here is an example. This is the same example as what we seen in the previous slide. And if you sort of look at the stack layout at the point of perform, it's going to look like this. So there is going to be this first fiber, which is running this bars, right? And because we are running bar under an effect handler here, so it is going to run under a different fiber, bar, and bar calls foo, right? So this is the stack layout. And we somehow have to explain to through dwarf, right, how to unwind the stack. And it turns out that dwarf is a Turing complete language, right? You can write arbitrary programs using dwarf. And we have some bespoke dwarf bytecode that knows how to follow this parent pointer and to find the rest of the stack. Okay, so this is all good. What do we get as a result? So if you run the same program under LLDB and you set a breakpoint on perform, right? And you get the backtrace, you get this backtrace out. And in particular, what I want you to take away is that we are performing, right? We see foo and bar, which was on one fiber. And then we have this run stack function, which is sort of the border between two fibers. And we also see baz on the same stack, right? So even if you have multiple fibers, multiple handlers on your stack, you can get the backtrace of the entire stack using LLDB and GDB. Perf also works out of the box, thanks to the way we organize this, right? So we are not breaking backtraces. And debugging and profiling is sort of often overlooked, right? So, and we sort of put in a lot of effort to make sure that we still preserve the nice properties that we have with OCaml. So, okay, so this is all good. So how does this actually perform? So we have a micro benchmark first, right? First, we want to see what is the overhead of actually context switching. So this program itself is very simple. So it installs a handler and the computation simply performs E, right? And we handle it in this handler, which immediately continues, right? Continues the continuation, and perform E has nothing to do after it. So it returns and the whole foo function returns. But I also have these strategically placed comments everywhere, right? What do these mean? So each of the instruction sequences, right, involve a context switch. In particular, instruction sequence A to B involves the creation of the stack for this new fiber and running the computation. B to C here involves performing the effect and handling the effect. C to D involves running the continuation, right, resuming the continuation. And D to E is when the computation runs to completion and then you free the stack, right? So each of these instruction sequences sort of involve a context switch, and we want to see what is the cost of each of these instruction sequences. And so we ran this program on Intel Xeon Gold CPU, 5120 CPU, right? And for calibration, the memory read latency on this machine happens to be 90 nanoseconds for reading the local NUMA node and 145 nanoseconds for reading a remote NUMA node. And we measured the time taken for these instruction sequences using parse cycle accurate counting ability. And the result that we see is that the time taken for doing each of these sequences is far less than accessing memory, right? In particular, since this is running at 2.2 gigahertz, it's around like less than 50 instructions for any of these, right? And this is a win. So context switching and installing handlers, performing and resuming are all really, really cheap, like in the small. Okay, so that is a really nice micro benchmark. So let's look at a larger one. So then what we are going to look at is generators. So this is the same program as what we have seen earlier in the talk. And what we are going to measure now is we're going to do a complete on-demand traversal of a binary tree of depth 25, right? And this is going to involve 2-part 26 stack switches, right? And we compare 3 different versions. First is the iterator version. So it's an idiomatic recursive traversal, right? Just to establish a baseline. We have 2 versions of generators. First one is the handwritten generator that sort of is the best that you can get for a generator. What it does is it specializes the code for the binary tree. It does CPS translation and applies defunctionalization optimization to remove any intermediate closures, right? That's sort of the best case that you can get. And we also have the generic implementation of generator using effect handlers. So the results are presented here. So the key takeaway here is that generators are in fact more expensive than just doing plain iteration, right? It's around 3.76 times more expensive. And effect handler generator is like even more expensive, right? It's around 2.5 times more expensive than handwritten one. There are 2 points to take away from here, right? So firstly, we are measuring pure overhead, right? If you have any useful work that you're doing in this program, then the overheads are not going to be so stark, because useful work should hopefully dominate these overheads and the difference will be smaller. And the second thing is handwritten generator was specialized to this tree, right? But the effect handler generator is generic. So this applies for all sort of iterators. So just to do another point of comparison, we compared against Node.js. We implemented the same program and we measured the performance of iterators and generator using the inbuilt primitive support for generators. And the main takeaway is that it is 90 times more expensive, right, than iterators. And it's around 10 times more expensive than the generic effect handler implementation compared to the primitive one that is part of this JavaScript implementation. Of course, we are comparing apples to oranges here, so take this number with a pinch of salt. But observe that the overheads are not are much lower compared to what other languages provide. So the last thing that we are going to see is what we set out to do, right? We are going to implement a full-fledged web server using effect handlers, right? And for comparison, we have 3 different variants. We have a Go variant using Net HTTP, and we set Go max procs to be 1 because we want to test the performance on a single core, right? And we have 2 OCaml versions, one using LWT and other using effect handlers, which we call MC. And the client-side performance was measured using this Vert2 workload generator. So here are the results. The way to read these graphs is that for throughput, what we've done is we first establish 1,000 open connections, right? And we sort of make requests on this particular web server. And we continue doing this for 60 seconds, right? And across the experiment, we slowly increase the number of requests that we make, and we measure how many requests were serviced, right? And across all 3 versions, you can see that the web server scales to around 30,000 requests per second, and then it plateaus out, right? So that gives us a throughput measurement. And for latency, what we did is, okay, we said we'll pick 2/3 of the plateau out stage as the point at which we want to measure latency. And we are measuring tail latency, right? So we said we'll establish 1,000 connections. We will keep requesting 20,000 requests per second over 60 seconds, right? And we measure the tail latency here. And the graph here shows that the multicore version performs better than LWC and Go, right? You can sort of I mean, it performs best, but that's not the point here. The main point here is that the 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 web server implemented using effect handlers is in direct style, right? There is no monad syntax. You don't have to program with monads, right? You can use OCaml exceptions, right? You can throw and catch exceptions. You get backtrace per thread, right? You get backtrace per request. So the thing that we want to do, which is to spawn a thread per request, you can do, and you can get a backtrace, right? You can essentially stop the web server at some point and then say, okay, get me the backtrace of all the open requests that are out there so that I can see where my program is actually spending time, right? And you can use GDB and perf to debug and profile your program, right? That's the main takeaway. Performance is important, but we can see that it's in the right ballpark. Okay, so that is all I wanted to say today. You can play around with Multicore OCaml today. The command is here. I also put up the slides on my website. You can take a look. There are lots and lots of examples, fancy examples with effects, which are available on that link. We've also written a couple of research papers on this topic. If you want to sort of have a deep dive into what we do, you can read these papers. But other than that, thank you. So thanks for listening.
Thank you. Excellent, excellent talk. Thanks so much, KC. If anyone would like to join us here on the stage and ask the question live, just please raise your hand so that I can hand over the microphone to you. I can see Manuel posted a question. Let's invite him here.
Hi. So you already answered one of the questions during your talk that you want to have I/O as an effect as well.
Right.
And I was wondering, I'm not very familiar with OCaml, but I'm assuming that there are different compile targets that you can have, probably. And well, all of them will come with different built-ins. And if you have an FFI that uses the built-ins of your target, then would make sense to maybe to have like effects that that correspond to the different built-in things that you can do in your specific language that you're compiling to. You could have different effects for those, but I assume that that's probably hard to do because you don't have any static check whether all your effects are handled.
We do, right? So I mean, a really good question. So you can define, so I showed IO, but you can also track user-defined effects as part of the type. So I mean, if you take our example, we defined an effect E, and if you have a function that performs E, you will have an annotation on the arrow which says this function is going to perform an E, right? And the top level, the contract that we want to have is that when you want to execute the program, it better be the case that arrow has no effects on top, right? The top level function. So we do have support for that. So this is sort of building on a long tradition of doing row polymorphism, right? So I think some of these pieces are already in OCaml, and we are going to reuse some of those pieces. So certainly, yes, we can track user-defined effects, and if different targets bring in their own effects, then we can track them as well.
But how is the effect then deleted in your program? Well, I don't know, but maybe a stupid example. You have a program that you want to compile to JavaScript or to LLVM, and you want to use the JavaScript logging something log on the console. So you have the log on the console effect. So when you want to compile to JavaScript, you have to leave that effect in there, but you cannot leave it in there if you compile to LLVM. That makes sense.
Yeah, I think I get this question. I mean, you sort of have to somehow in the build system, right? So you have to say, okay, if I have a log effect, what I'm going to do is to wrap this log effect in, say, JavaScript function, which is going to erase all the effects out, right? It might not do anything. It might just say, I have some magic that I know, which is going to erase out log to console, but not anything else, right? So, and that is the function that you actually use to target JavaScript. Of course, you need some sort of a wrapper, right? So this is doable, but it's sort of you have to have a special function, one function for each of the targets that you're going to compile, and you wrap the program around that function.